Hi, welcome again. I hope you will be performing good at your homes. Today, we will be starting with the water application in the food. In the previous lecture, we have seen the discussed the some of the properties and the chemistry of the water. Now, today we will be based on that properties. We will be looking how we can use that knowledge for the application in foods for the preservation, especially for the preservation point of view into the foods. So, as we have already discussed, that the water that combined through the hydrogen bondings, different water molecule you can see here that are combined with the hydrogen bonding, and this hydrogen bonding have a great impact on the properties of the water. Individual covalent bonding and the angle for the hydrogen and the oxygen that is also have an impact on the properties and application of the water. So hydrogen bonding and the covalent bonding and the angle between these hydrogen and oxygen, that is very important for the properties as well as the application point of view. So as you know that the water that is the predominant constituent in many foods, while you are uh, talking about the fruits, vegetable, meats, grain product, all have the certain level of the moisture content, and on the basis of that we can call them as some of the product that is the perishable product, some of the product that are the semi-perishable product, and some are the product that are having the more shelf life. So as a medium in these product, in these food product, as a medium, water supports the chemical reactions, and it is a direct reactant in hydrolytic processes. Therefore, the removal of water from food, binding it by increasing the concentration of common salts or sugar. There are so many ways by which you can bind the water in the product by means of the common salt, by means of the sugars, and the common salt and the sugars. Uh, these are being used, these are the substances being used for the preservation of the food item since centuries. So, the basic purpose is to control the moisture content that will further inhibit the growth of the microorganism. So if you control the microorganism in the food product by controlling the moisture content, it means you are increasing the shelf life of the food products. Now the water that, if you look at the composition of the food, because the food is a complex mixture of the different constituents that may contain protein, polysaccharide, carbohydrate, lipids, salts, moisture, water content. So all of these are having significant effect on the texture of the food, on the properties of the food, on the preservation of the food. So as we talked about that the simultaneous presence of the two acceptor sites and the two donor sites in the water that permits association in a three-dimensional network that are stabilized by the hydrogen bridges, and this structure which explain the spatial physical properties of water that is unusual for the other small molecules. We have talked about that. These have different behavior of water as compared to other components. So we will be talking about the impact of the water on the food with respect to its storage life, with respect to its preservation. So there are so many techniques for the preservation that is being used in today's world. If we talk about some of the historical perspective, so drying and the low temperature storage, these are the one of the oldest methods of the preservation of the food containing the high water content. So the modern food technologies that tries to optimize these methods to bring about new novel changes, new methodologies. So a product should be dried or frozen only long enough to ensure wholesome quality for a certain period of the time. Naturally, drying and or freezing must be optimized for each product individually. It is therefore necessary to know the effect of water on storage life. So in today's research, there is a focus that every product, as we know, that have the variable amount of the moisture content. So the preservation technique that should be focused on every food product having variable amount of the moisture. So one of the technique that the preservation take up, that is the use of the water activity, knowledge of the water activity. How we can define this water activity? Water activity is basically a ratio of partial vapor pressure of food moisture at the certain temperature T and saturation vapor pressure of pure water at that temperature. Alternatively, this water activity that can be defined, that can be calculated on the basis of equilibrium relative humidity at a certain temperature. So ERH, equilibrium relative humidity, is divided by 100. That will give a ratio of water activity. So this graph that is very important, providing a baseline to understand how the different reactions that is happening into the food and how different factors that is affecting the food based on the moisture content of the food. So before going to that, you must have a knowledge about that. In the foods, there are different components or different kind of the reactions as well as different kind of the microflora that is affecting the shelf life of the product, its deterioration process, its self-destruction process, its enzymatic type of the biological reactions, its chemical type of the reaction. So all may happens into the food product having different texture, having different moisture content. So the relationship between water content and water activity is indicated by the absorption isotherms of a food. At a lower content, even minor changes in this parameter lead to major changes in the water activity. The effect of water activity on the process that can influence the food quality is presented in this uh, figure that is presented in this figure. So look at this one. At the x-axis there is the water activity 0.2, 0.4, 0.6, 0.8 and 1. The pure water have the water activity of 1. So we can see that most of the bacteria most of the bacteria that have a water activity above zero point 0.9, you can see above zero point 0.9. So it's mean the if the food products that will have the higher water activity, the bacteria that will be growing in it, and by certain processes, by you are making unavailable that water by salting process, by adding the sugars into it, by drying process, by freezing process. So if you are using any process that is reducing the water activity below zero point 0.9, It's mean the most of the bacteria that are controlled, that will not grow on that food. So if a product that will have a here a water activity of this one, a water activity of this one, it's mean there is no chance to grow the bacteria. Most of the bacteria that will be not grow on that, so the product will be preserved for the bacteria. So look at this behavior of the bacteria. As the water activity is increased, the growth of the bacteria that is going to increase. You can see if the water activity is going to increase, the growth of the bacteria that is increasing. And if the water activity is going down, the growth of bacteria that will also go down. For the yeast, if certain product that have a problem of the bacteria and yeast, certain food products have only the problem of the bacteria, certain food products have the problem of the bacteria and the yeast. So how you can control that? We can see that the yeast product, most of the yeast attack that happens at zero point 0.8 water activity are above. You can see this can be most of the yeast activity that can be in between zero point 0.8 to 0.9 or certain level above to that. So it means that the yeast can be best controlled if the water activity is below zero point 0.8. Below zero point 0.8. Again, you can use some of the preservation techniques, lowering the temperature, freezing point, so that less water is available, by salting, by sugaring, or some other technique. So the lowering the water activity will lower the chance of the yeast growth as well as the bacterial growth. So if the problem is bacteria, yeast, and the fungi, you have, because the fungi are more tolerant to the lower water activity. So you have to lower the water activity up to zero point 0.7. So you will lowering the chance of this, all of these one. So of all of bacteria, yeast, fungi that can be best uh, preserved if the product have the problems with the bacteria, yeast, and fungi, that product that can be reduced to water activity of zero point 0.7, so that there will be less chances of the growth of bacteria, yeast, and the fungi. These are the biological type of the spoilage agent. So we can say that the biological type of the spoilage agent that can be preserve the food product that can be preserved if we are lowering the water activity to about 0.7, right? So what about the things that are naturally available? These are the things that are actually attacking the food item from the outside source. But what about the things that are naturally available into the food products? Enzymes are naturally available. These chemical reactions that is naturally occurring into the food product, lipid oxidation process, these are due to the internal contents of the. So for these chemical and the biological reactions, biochemical reactions, you have to go for much lower water activity. Enzymatic, as we can see that enzymatic uh, activity that are actually dependent on different kind of the enzyme. Each enzyme that will have a different properties, different characteristics. So you can see enzymatic activity that have a very big range of water activity at which these enzymes that are working. So look at this one. About zero point 0.3 to zero point 0.7. It's a too much big range, you can see, in which these enzymes are that can work. So to avoid the complete enzymatic activity, the water activity that should be below zero point 0.3, and this can be only possible when you are freezing. You come across that the peas, green peas that are sold in frozen form at most of the time. So by freezing, you are lowering the water activity below zero point 0.3. So you are controlling the enzymatic activity in that case, fungi control, yeast control, bacterial control there. And if in a product, food product, you have to control the non-enzymatic browning. So look at this one, the graph that is very typically different from other enzymatic activity fungi, bacteria, yeast. So look at this one, non-enzymatic browning first going to increase up to the level of zero point 0.7 water activity. Then further dilution process that will again decreasing the non-enzymatic browning reaction. These are the most of the time chemical reactions. So that has a different behavior. So either it's a best practice to lower the water activity below zero point 0.2 if the problem is the non-enzymatic browning in the product. Same is the case with the lipid oxidation process. Lipid oxidation process is a very complicated process, and you can see the behavior of the lipid oxidation. First of all, when you are increasing the water activity, the lipid oxidation process that goes down, but above zero point 0.3 water activity that starts to rise up till zero point 0.7 water activity and then slightly decline. So on the basis of the information of that, if the problem have the lipid oxidation problem, so you can accordingly control that one. So decreased water activity retard the growth of microorganisms as we have seen in the previous graph, slow the enzyme catalyzed reactions, and lastly retard non-enzymatic browning. In contrast, the rate of lipid auto-oxidation increase in the dried food system, as we see in the picture, in the graph, previous graph. Foods with water activity value between zero point 0.6 and zero point 0.9, these are known commonly as intermediate moisture foods. Because most of the problem you can prevent by controlling in this range the water activity. These foods are largely protected against microbial spoilage. One of the options for decreasing water activity and thus improving the shelf life of food is to use the additives. These additives are commonly called as the humectant. Actually, what these humectant are doing, these are binding the water, making the water unavailable for the microorganism in the reactions. In addition to common salt, what are these? The example of these humectant, common salt, as we know that common salt is being used for the preservation for centuries. Other humectants are glycerol, sorbitol, sucrose, again the sucrose that is being used from centuries. So all of these are the example for the humectant for binding the water molecules so that to increase the preservation capacity. However, they are also sweeteners and would be objectionable from a consumer standpoint in many foods. In salt, you cannot add the sweetener for preservation purposes. In vegetable, maybe you will not like to add the sweetener for the preservation purposes. So in the concentration required to regulate water activity, this is also important. Another thing based on this knowledge, I have told you earlier that the new research is being in process to use the new things to determine the preservation behavior and based on the water activity, based on the water content of the foods. So that what are the new things? What are the new researches on that is increasing for each kind of the product, for each type of the food product, the different behavior uh, will be. So to understand that, each type of the food item that will be researched on. So phase transition of the food containing the water, that is today related with the food preservation process and based on the water activity as well. The physical state of metastable food depends on their composition, on temperature, on storage time. For example, depending on the temperature, the phases, now these are the basically terminology that is being used for the phase transition and the DSC, differential scanning calorimetric technique, that is used to determine the phase transition process. So what are these terminology? When you are using this differential scanning calorimetric technique, DSC technique, you will be using the terminology just like the glassy, rubbery, highly viscous. These are the terminology that is commonly used for this. Uh, so in the next slides, we will be looking at the thermogram, and you will be well aware of these terminologies as well. So the kinetics of the phase transition can be measured by means of the differential scanning calorimetric technique, DSC, commonly called DSC. This equipment that produces a thermogram that shows temperature Tg, Tg means glassy temperature, is the characteristic value for the transition from glassy to rubbery. Food become plastic when their hydrophilic components are hydrated, and thus the water content affect the Tg value. For example, we will be looking in next figure. For example, in the case of the gelatinized starch, we will be looking at that one. So look at this. This is a typical thermogram. It's a typical thermogram for a food product. Now look at this one. As I told you earlier that the water activity can be, control of the water activity can be used for preservation of the food product. So look at this one. Uh, we have two options here. We have two options here. This is the temperature. This is actually the water content. So we have two options. Either uh, you subject that food to the higher temperature so that the product that is coming into the glassy state. This is a temperature at which this product that is coming at glassy state, but this is an ideal condition that is achieved with difficulty. Another ideal condition is to lower the temperature, minus 100, minus 135. So this again the glassy temperature at the lower temperature, glassy state at the lower temperature, but you know that 135 temperature, that is very difficult to achieve. A lot more resources that may be required, right? So this is the condition with 100% of the water is there, but in the frozen form, and is not available for reactions and not available for the microorganisms. But you know the water is present in 100% in the form of the ice. Here the water is, all the water have been evaporated from the food product and the water is at 0%. It means you completely going to dry, but these are difficult. Completely drying, that's very difficult. So we have two conditions to achieve this glassy state, either at 0% moisture content or keeping the moisture content to the maximum. So both are the possibilities with you. So in the intermediate, this is the phase transition. This is the phase transition. The one show maybe from one phase to that is shifting into the other phase. So what will be the, if this graph is thermogram is generated for each product that will be a, there will be a different thermogram. So look at this one. This will be a glassy temperature that may be achievable, and you can see that still contain 25%, almost 25% of the moisture. So with 25% moisture, the food product that can be, this food product that can be preserved safely at 0 degree centigrade, still containing the moisture content in it. You are not drying completely. You are not having the 100% of the moisture. So this thermogram that tells us what is the best combination for this phase transition at which the product that will be maximum shelf life. So the quantity of unfrozen water at this temperature is about 27% by weight. You can see here about this is the 27%. This is the unfrozen water. So we will, if I have given you the book of the Phonema food chemistry. So if you look at the chapter on the water, chapter on the water, and you look at the table number point 7 in that chapter, Phonema food chemistry, on the chapter of water, table number point 7, that lists the temperature of TG temperature for aqua solution, 20% by weight of carbohydrates and protein. In case of the oligosaccharide in that table, I will strongly recommend to see that table. Oligosaccharide composed of 3 glucose molecules, maltodextrose has the lowest TG value. So that table that shows the different TG values for different kind of the food material, and based on the chemistry of the sum of the substances, the TG value of certain substances. So you will have an idea how these can be preserved at what kind of the temperature, what kind of the moisture content in it. So the reason is probably that in aqueous solution, the effective chain length of linear oligosaccharide is greater than that of the branch compound. So different starches will be different. If the starches will have different amylose to amylopectin content, there will be different parameter for the TG values. So that's all for today for the uh, chapter on water. I hope you will be uh, reading all of these chapters as well as looking at these videos as well. And with this, I will close this chapter and hope to see you in the next lecture. Thanks and goodbye.